Okay. Yeah, so hello everyone. I'm Wenting. I'm here to present my work on making a really fast e-ink controller. So I guess, first of all, just a little bit about myself. I'm currently a full-time SoC designer at Zero ASIC, kind of just working on RISC-V CPU, these kind of stuff. It was located in Cambridge, Massachusetts. I'm also a part-time student at Tufts University. In the past, I've done other projects like a Game Boy implementation or a superscalar RISC-V cores, among many other projects. So let's get into today's topic, which is about e-ink. Let me first give some backgrounds in case you don't know what e-ink is or don't know how e-ink works. So e-ink is actually a brand of a family of paper-like electrophoretic displays. It was invented in an MIT Media Lab a few decades ago. And nowadays, they are commonly used on e-readers and electronic shelf labels. You've probably seen them mostly on Kindle, that's e-readers, or in stores in like shelf labels showing the price, train stations, maybe showing when is the next train, or maybe even in airport restrooms. Why not? The basic concept isn't hard to understand. In the simplest form, you have charged particles with different colors, one white, one black, and it was dispersed in some sort of oil-like thing in some transparent container. And if you just apply some voltage or electric fields, then the particles can be moved up and down to produce either black or white, or a mixture of that. Of course, turning this concept into an actual mass-produced display, it's no small feat, but that's kind of outside of the work that I've done, so I wouldn't go into details about that today. In terms of display quality, because it's a display, we kind of want to compare it with other screens. They are unfortunately no match for modern IPS LCDs we found on laptops. Don't even talk about OLED. It pretty much worth everything in every perspective possible, and it's also more expensive. So now the question is, why would anyone bother with that if the display is so bad? It does have a few advantages, but not in the display quality. It reflects lights instead of emitting lights. So it generally consumes less power because you don't need a front light or back light to emit light. And so which means it can be used outdoors under direct sunlight, etc. It's also bistable, means if you disconnect the power, it will retain the image before you disconnect the power. But for me, like personally, the biggest differentiating factor for e-ink is it looks really like a paper. We have many other display technologies that like listed one here. Some of them are reflective, some of them are bistable, but none of them feels like paper. So if you really want a paper feeling, then e-ink is a technology to go. So the focus goes back to e-ink, which is, we know it's a nice paper-like display technology. Personally, I would really love to try to use e-ink monitor for writing and coding, etc. Sounds like it will be a perfect fit for e-ink, right? So turns out, sure, many thought the same. So there are already a bunch of e-ink-based typewriters and monitors on the market. You probably recognize some of them. Personally, I actually bought and tried out most of them. But all of them share a common issue is they are slow. They are still usable, but I found using them unpleasant at the very least. So there got to be a way to actually improve it. So I started my journey. First, let's start to understand how slow existing products are. I bought an off-the-shelf e-ink so-called high refresh rate ink monitor and costing almost $1,000. Then start comparing LCD side by side for latency. So you see in these diagrams, the purple trace is LCD, and then the yellow trace is e-ink. Just two monitors side by side, and then comparing how fast they can respond. And I got some interesting conclusions. So one is the screen itself is slowish. You can see the ramp on the yellow is much slower than the ramping on the purple, which is LCD. But it's not that kind of slow. The ramp on the e-ink is about 100 milliseconds. And then you see like this is across multiple runs. Sometimes e-ink is relatively fast, like on the lower right. Sometimes it's really slow, like upper left. And that's the controller delay. So when a PC sends your information to the ink monitor thinks about it and then processes it, finally display on the screen. So it turns out on existing monitors, like how much latency you got from the monitor is actually a lottery. Sometimes it's fast, sometimes it's slow. On the fast side, I measure 60 milliseconds. Slow side, I've measured 240 milliseconds. That's just based on luck. 60 milliseconds, that can be acceptable, but 240 is absolutely brutal. So can I make it faster? Of course I can, otherwise I wouldn't be here. I cannot change how fast the screen or how slow the screen itself behaves, but I can reduce the latency on the controller. The deal is that I will have to design my own controller. So starting from the basics, I have a basic controller matching their offerings, then I can start to see how I can improve it. That's my plan. Okay, so building a controller, then what is a controller? The job of a controller is to format the incoming image or video, generate the necessary interface timing, so the image would be displayed on the screen. Of course, it will be displayed a little bit different because it's a monochrome screen. That all happens inside this controller. And how to do a controller, we should start from the basic concept. The color of pixel, as I said, it can be changed by applying a positive or negative voltage for a finite period amount of time. From the controller's perspective, depending on the current state of the pixel and the desired state of the pixel, like it's white to black or black to white, there are 4 possibilities. The controller just needs to make the decision based on the color for each pixel, and that's it. To implement it, the color for each pixel needs to be stored somewhere so the controller can remember and then make decisions based on it. So a buffer memory is added with DMAs, moving data in and out of it. There are also a timer so it doesn't underdrive or overdrive the pixel. That's pretty much about it. And now I have an ink controller. And it works. But it only supports, so far it only supports black and white, no grayscale in between, because you see that table, there's only 4 possibilities. So I couldn't quite display picture or anti-alias text yet. And that's the next step. This can be solved or mitigated in 2 different ways. One is you add a dithering step in the image processing pipeline to dither the input image to be binary only by using these dots, change the density of the dots, so you kind of feel it's grayscale, but it's actually not. It doesn't look too good either, but it's better than nothing. So is there a way to achieve actual real grayscale? Of course there is, and it's quite a simple idea. The idea is by underdriving the pixel, because you see the pixel takes 100 milliseconds to turn from black to white. What if we just stop in the middle? Then we get gray. That's pretty much the concept. And on the right, I have a proof of concept I did using this method, showing it actually works. Up to 32 level grayscale even, that's kind of beating the current ones, show it's possible, with some caveats, of course. So I said this is proof of concept because this is actually not the method used on commercial devices. The commercial devices, they tend to do it more complex. It's more than just simply underdriving it. It actually involves shuffling the pixel from black to white several different times, finally settle down on a value that works better like across large range of screens, larger range of temperatures. So they did that. And then to avoid coding, like hard coding all these complex logics into the controller, what E-Ink does is they just do a lookup table called the waveform table. If you know about E-Ink, you probably heard the word before, waveform. It's really just a lookup table. The controller uses the same information as before to look up the table. The table then tells the controller, should it apply a positive voltage or a negative voltage or apply nothing, which is common voltage around 0 volts. The content of the table is provided by E-Ink. So as a user, I don't really need to worry about it too much. And implementation-wise, it's actually easier. I just replace the previous logic now with a lookup table. I don't even need to code anything. And I'm basically done implementing an E-Ink controller matching the existing ones. So this is pretty much the controller inside of these $1,000 E-Ink monitors. And by changing, because now it's now a lookup table, by just changing the content of lookup table, I can do things like clearing the screen. If I say the lookup table is, I don't care about input, just always clear the screen, then that's a clearing screen. Or I can switch between binary and grayscale mode. If you load up a lookup table, just completely ignores the color information or grayscale. In between, you get binary output. If it looks at it in grayscale, now of course you get grayscale. So now I have a basic controller design. I can start to analyze why it's slow. As a start, as I said, grayscale is slow because I need to go black and white back and forth to modulate the color, so that's obviously slow. But the binary is just like one shot to the desired color, so binary is obviously faster on the e-ink at least. So in many cases, even though we do have native grayscale support on e-ink, unfortunately, like binary with dithering is still preferred. This part has been figured out by existing devices already, and they all use binary plus dithering in fast modes. So if you go and look at these faster e-ink monitors where they show they can play videos, you can play games, it's actually just all dithering. There's no grayscale. But then you see, like, I already did the measure. Binary on these screens are so slow. Why is that? We already know the screen takes 100 milliseconds to respond. So we say at 60 hertz refresh rate, that's 6 frames, then the problem is the controller will basically ignore any input in this 6-frame window. So it can only display up to 10 new images per second. And worse is if your input changes within this window, it's not going to start processing this input until the next period starts. So we're talking about worst case 100 millisecond output latency. And in actual devices, what they do is a screen and their input engine even runs asynchronously. So then you just have more buffering delays in these devices. So, but then we say, okay, ignore all these things. It's 10 frames per second. That's still pretty bad. It can be good enough for an e-reader, but then it's horrible for an ink monitor. And then I said the monitor I bought is a so-called high refresh rate monitor. What does that really mean? What it really means is they have a dial to control the speed. They have fast mode, fast plus mode, fast plus plus mode, all these kind of stuff. What the dial really does is it intentionally underdrive the screen, not for grayscale, but to improve the frame rate. So then you can, instead of like a 6-frame period, it becomes 3-frame period, and you get 15 to 20 FPS. The cost is you're not driving the screen fully, so the contrast is lower. And to be honest, 15 to 20 is not good either. It might sound like a dead end, the screen is just slow, what can you do? But it's actually not. Learning from others, there are some commercial e-ink controllers found on e-readers that support something called multiple update regions. So imagine the user is typing, like using an e-ink monitor and typing on the keyboard. The user types letter A, then followed by letter B, say 15 milliseconds later. With the basic controller, the letter B wouldn't start being displayed until letter A is fully displayed. So we just, waste some time there. B doesn't need to wait for letter A because they are on different part of the screen. If the left part of the screen is displaying A, it doesn't stop from right half the screen to start displaying B. So the reason it was waiting is really the controller itself has a timer to keep counting, okay, how many frames have driven the pixel, how many frames left, I still need to drive it. It was sharing a global timer for the entire screen. So that's why I had to wait. And I decided to simply move the time counter value into part of the pixel state. So store alongside with other color information, you already need to store what the color is. Why not just store your timer information there as well? Effectively, now each pixel is in their own region now. So you no longer have these kind of waiting situations. This improves the typing experience by a lot. But this approach is still not perfect. Say if I type letter A, and then that was a typo, so I need to delete it and type letter B instead. In a naive implementation, I need to wait for the A to fully appear, then wait for it to fully disappear, and then finally wait for the B to appear. That's just a lot of time. And by simply moving the time counter to local, as previously did, doesn't really solve the issue, because they are no longer on different parts of the screen. They are on the same screen, or we're using the same timer. But then, by leveraging the timer, we actually know how much we've driven it, and we can just reverse it by taking a look at the timer value and decide how much we actually need to reverse it. With this, the typing is quite smooth right now, though unfortunately I couldn't really show you the typing latency, because you kind of have to come to our demo booth there to feel yourself. But I can show you a clip of Bad Apple playing. The latency is minimum, even comparing to an LCD side by side. Then, when looking at the latencies, now we'll go back to the oscilloscope to see how much we actually improved. The difference is quite stellar, because the controller is always responsive, and there is no input window or additional buffering going on. The input always goes to the screen straight, giving a consistent 50 millisecond latency. This is still not good, but it's more or less of a screen limitation right now, which I couldn't really solve on my end. But there's more. There's always more improvements I can done. Actually, using this monitor, like I use it daily and reviewed more issues. Let's just take a very quick look at them as well. One particular issue is if you move the mouse cursor too fast, it actually disappears, because the controller now no longer waits for a screen. It always drives the screen to the input. If the input doesn't change, it allows the screen to respond. If the input changes, it just changes as well. So if you have fast-moving things like a mouse cursor, it just disappears. But of course, this can be fixed. And to fix it, I had some logic to ensure like each pixel is driven for at least 2 to 3 frames. Turns out that's a quite effective fix. Unfortunately, like a mouse cursor, it's kind of too small. And then another issue, go back to the grayscale thing. I said the grayscale is slow, and all of these e-ink monitors still offers grayscale because it's true grayscale. It looks good. While it looks good, you see the user experience is pretty bad. It's basically unusable. It flashes too much, and it's way too slow. Then, okay, how does everyone else get away with this problem? There are e-readers with grayscale, right? How did they do it? What's the solution on existing monitors? Can we learn anything from them? On e-readers, it's actually not a big issue because the software can always switch between fast and slow modes based on the user interaction. Because the e-reader, you have the software there, the software knows what you want to do. And it may simply not offer any operations that just doesn't work on e-ink. For example, e-readers, they don't offer scrolling. They always want to do a full page flip because that works better on e-ink. Then, okay, that's not an issue for e-readers. What about e-ink monitors on the market? What they do is they just throw the problem back to the user. Basically, the user have to accept the update is going to be slow, latency is going to be horrible, and the process is going to be flashing. I mean, it's just a price to pay to get better image quality, so that's what I did initially as well. You see that video. But after using it for a while, I cannot use it. I have to do something better to actually fix it, for it to be useful at least. What I come up with is allowing it to switch between the fast binary mode and the slow grayscale mode automatically on a per pixel basis. When the input image is changed, it switches to the binary mode and do all the it would be really fast, right? And then when the image hasn't been changed for a while, it re-renders the image in grayscale. This is a bit extreme demo, so you can see the process is a little bit chaotic. But with this hybrid mode implemented, I've personally found it to be much more useful. And the mode is especially suitable for reading PDFs, where your page turns is usually infrequent, and you really want to get good image quality, but sometimes you just do need to flip through pages really quickly to find the thing you want. So far, I've been focusing on monochrome ink screens, but there are a lot of hype around color e-ink screens. So let's take a look at them as well. This is actually, like, I think, one of the most requested features once I do it. So let's take a look. How is color e-ink doing? Here is a list of all the full color e-ink product lines that e-ink has offered up to date. That's a lot. Based on their underlying technologies, they could be divided into two categories, and we have to look at separately. One is using color filter array, another is using multicolor pigment. And let's just look at them one by one. The first is color filter array. That's a simple idea. You just add a colored glass or a film on top of the monochrome screen pixel. This is pretty much the same technique used on LCD as well. So now the light become colored. Of course, you get a color screen. And it does have a lot of benefits. So from a screen driving perspective, it's just the same screen. It doesn't know you have a film or colored glass on top of it. So it really just the pixel is now color. The refresh time stays the same. So everything I talked about, like high refresh rate, all these tricks or improvements, they just applies. And each subpixel, you still get 16 level grayscale. So that would give you 16 cubed equal to 4096 color display. One thing that worth some discussion is the resolution for these color screens, because it's you kind of each pixel can only get one color, right? And this is example I took from one of the color e-readers. They claims 300 ppi of monochrome resolution and 150 ppi for color resolution. Why that? Well, that's what I said. Each pixel can only be one color. So use this first generation e-ink Triton 1 screen as an example. You see this is under microscope. Now you can see like pixels, some pixels stays white, some pixels become color. And for them, each color pixel divided into 4 subpixels, RGB and white. The monochrome version of the screen has a resolution of 2K, that's 2560 by 1440. But since now each monochrome pixel becomes a subpixel now, and the color version only has a resolution of 1280 by 720, 1/4 of the original resolution or half of the PPI. Then let's start thinking, okay, if it's really a 720p screen right now or half the PPI, wouldn't be like lying for them or false advertisement. They still say, you know what, the monochrome resolution is 300 ppi, not 150. Well, it turns out there is a technique called subpixel rendering. It's also commonly used on PCs as well. Microsoft calls it ClearType. There is also subpixel anti-aliasing you can turn on Linux. I don't think macOS does that, but anyway. The thing is, your pixel can still convey additional luminance information. So if you leverage these subpixels, you can still get better text result. So it's fine for them to call it 300 ppi. This just explains what does it really mean for color resolution and the monochrome resolution to be different. So far, it sounds like this sounds a reasonable technology, a reasonable upgrade on top of a monochrome screens, but it has drawbacks. So the major drawback is the filter, the color filter. Obviously, it filter out some light, actually a lot of light. So the screen ended up being quite dark. So I said, this is white. This is a Colorido 3, their latest color screen, displaying white. Obviously, this is not white, but because it's filtering out so much light, this is the best it can do. And it's possible for you to trade in some color saturation for high reflectivity, but there is only so far you can go before the color becoming too washed out to be meaningful. For example, I showed here, you have one side, you have color screen, which is monochrome. Color gamut is nothing, it's black and white. You get 45% of reflectivity. And to the latest Colorido 3, you pretty much like 1/3 of the reflectivity, 15%, and you get 11% sRGB gamut, which is laughable already. And then there is in the middle where you can do some trade-off. You get 24% reflectivity kind of in the middle, and then your color gamut drops down to 1% sRGB. At some point, you really start to question if this is still a color screen or not. But this is kind of what they can do with color filter array. So I said there were 2 different ways if you can do color. So what about the other one? That the multicolor pigment-based ones. On the right, that's a multicolor pigment. Well, what's that? The idea is simple. So remember, each capsule, it has black and white particles you can move around to generate different color. Well, of course, we just add more particles and let them to be different colors. And if we can shuffle them around to generate the color, then that's perfect. That's what they did. So the limitation is you still have only two electrodes, like one on the top, one on the bottom. You can only still apply one voltage. How do you use one voltage to control 4 different particles inside? So what they did is they would, these different particles, they will have different charge, they have different weight. Like some are heavier, some are lighter, and some would have like threshold voltage. If the voltage is too low, it just doesn't move. With all these combined and a very elaborate driving scheme, they can get colors with just 2 electrodes. And the result is actually quite impressive. Just look at it. You wouldn't even think the left one is color if you do this comparison. But it's not perfect. If it's perfect, we would be seeing them being used all over the places. There are 2 main issues. One is grayscale, another is the speed. Unlike the color filter array-based screens, where you get 4,096 colors just by combining 3 colors, multicolor pigment screens officially can only display 6 to 8 colors. And when I initially saw it, wait a minute, this couldn't be true. E-Ink has been advertising 60,000 colors everywhere. If you just go to their website, go to their Eshe, they say 60,000 colors. But actually, it turns out if you read carefully, it's 60,000 color gamut on the number of colors. They just trick you, like they played a word game, they're kind of. And which means there is no grayscale. If you look up close, all these fancy gallery or spectra screens from E-Ink just shows pretty heavy dithering. Though it's possible to hack the waveform to get more colors, like hundreds, but I'm still playing with that, so I'm not going into details today. Another limitation is the speed. It takes a quite long time to move all the particles to their desired location. For example, the original gallery screen takes 30 seconds to refresh, and the latest Spectra 6 screen, which they are advertising, takes 12 seconds to refresh. E-Ink also tried to roll out a faster version of the screen, namely the Gallery 3, if you've been following closely on the E-Ink. They want to push this technology for e-readers as well, and they claim the Gallery 3 can reach 1 second of refresh time, but what's the trade-off? Of course, there got to be a trade-off. They trade in color saturation for that. Again, underdriving the screen so it can be faster. And then the left is what they have, it's fast. On the right is what the gallery or this screen really could do, and you compare, okay, now you get washed out colors again to a point where it's only marginally better than the color filter array screen that we kind of disliked. Then this is really kind of missed the point. So the conclusion is there are different color technologies, but we don't have one single best color E-Ink screens yet. So that's about it for the color discussions. Let's go back to my design. Just take a quick look at the whole finished controller design and implementation as well. The design currently has been implemented on a Xilinx Spartan 6 FPGA. At the moment, it uses 2.6 kLUTs and can be clocked up to 70 megahertz, providing a 280 megapixel processing speed. So that really just relates to how big the screen it can drive. On the board level, I added more external components to make it a complete monitor, so you can use it. It supports both USB-C and DVI input. I have bridges for video interfaces, so FPGA can receive them. I also add a RP2040 microcontroller there for all the housekeeping items, such as like bitstream loading, decoder initialization, USB communication, USB-C, out mode negotiating, all these kind of different stuff. Just throw them into microcontroller. And in the actual layout, there are a few more things compared to the previous abstract block diagram. There are many power supply chips for both FPGA and the e-ink screen. The USB-C input also, it's just more than DisplayPort. If you want to go into that detail, basically the board needs to tell the computer it's a monitor. It expects DisplayPort input, and also it marks the right data lanes. So if you plug the USB cable in all directions, it automatically swap in the data lanes to make sure it always works. So that's pretty much about it. The end result is I have this fully functional ink monitor that's, I believe, more usable than anything else currently on the market. All the source code, including the FPGA RTL code, or the microcontroller firmware source code, or the PCB design, which is designed in KiCad as well, they are all open on GitLab. Just feel free to take a look or reach out to me. And if you want to see it in action, we have a demo booth there. So thank you for listening. If you have any questions, let me know.
Yeah, my question was simple. Do you have, what are your goals in your controller design? What are you trying to, I know you're trying to make it faster, of course, but any other constraints, power budget, size, something, whatever, complexity?
Yes, there are. So one of the constraints is, as you mentioned, NVIDIA GPU. That's a very good thing to bring up. That's something I consider as well, because by the end of the day, you're just processing pixels. And what's good at processing pixels? That's GPUs. You can just write a pixel shader that does everything that I did as well. Then you impose like a limitation of where it can be used. And also, you kind of need some additional software to go into your stack. Power consumption is also a thing, but mobile GPUs, that's kind of better. In general, like I want to create something that works for all sort of different platforms, which means there will be minimum, especially you think like, that's not a goal. Like doing everything from scratch is not a goal. The goal is for it to be compatible with different things with minimum additional work required to get it working. Say if you want it to be Android, because this sits like pretty down low level in your display stack up, you will have to hack DRM to get this working. And we don't want to do it. We don't want to provide hacking solution for each operating system. You need different things. For Android, for Windows, sits in between the display driver and Windows Window Manager or Linux Window Manager. That's a whole lot of things to do. It's much easier, just put all these things into FPGA, then present it as a standard monitor that you can plug in. Yeah.
Could you elaborate a little more on what made you change, make the move to RP2040?
Well, the actual reason for move to RP2040 was this. This is the stuff I was working on during pandemic, and RP2040 is the only thing that's in stock.
I see that you have a USB-C input there. So is that carrying a DisplayPort?
Yes, it's DisplayPort.
Last time I checked, it's very hard to find implementations RTL for DisplayPort. So what reference implementation in the RTL are you able to use?
Yes, so far what I do with this report is I actually just add it, it's actually right here, it's easier to show here. I have this PTN3460, which converts this report to LVDS, so that's much easier for the FPGA to work with. One reason is this just makes things easier. Another reason is to be able to receive DisplayPort is a pretty fast interface, like several gigabit per second. You really need a FPGA with a high-speed transceiver. And FPGAs with high-speed transceivers are much more expensive than ones without. So the price difference is more than just adding a few bridge chips. So I did bridge chips. But I do envision, like in the future, we'll still go with FPGAs with transceivers, because that would allow higher resolutions.
This is more of a material science question, but perhaps you know. With the manufacturers, have they tried heating pixels like to get faster responses?
Actually, with heating, you get slower. So I didn't have a curve here, but basically, with the current display, they really optimize it for working at room temperature. If you go like higher temperature, actually make it slower. If you go lower temperature, also make it slower. But yes, actually, in terms of material, if you're interested, so what E-Ink is currently doing is, maybe you heard, it's something called oxide TFT. That's not with the material itself, but more or less on the underlying driver circuit. So the driver circuit is what's currently limiting the voltage that can go into it. With the current TFT implementation, the highest voltage they can put onto a pixel is 15 volt. But with new materials, they can push this voltage higher to 25 volt, which should improve things a lot.
Could you talk a little bit about your test setup for how you did the latency trace comparison?
Yes. So the test is really simple. So I have a monitor. I have a laptop connected to two monitors, one LCD, one E-Ink. I didn't show it here, sorry. But I have a oscilloscope connected to basically two photodiodes put in front of both screens. Then I change the input so both screens will change. Then I can do a trace on the photodiode output. OK, thank you.